Every atom in your body, every breath you take, every beat of your heart, these are not just fragments of Earth's history, but relics of cosmic violence on a scale beyond comprehension. Long before life stirred on our planet, the universe was busy crafting the very ingredients that would one day make you possible. Picture this: a star, hundreds of times more massive than our sun, reaching the end of its life in a cataclysmic explosion so powerful it outshines entire galaxies. In that blinding flash, elements like carbon, oxygen, and nitrogen, the building blocks of life, are forged in the heart of the inferno and scattered across the cosmos. This isn't science fiction. It's the story of how supernova, the most destructive events in the universe, became the unexpected architects of life itself. For decades, we've marveled at the beauty of the night sky without fully grasping its profound connection to our existence. But what if I told you that the calcium in your bones, the iron in your blood, and even the oxygen filling your lungs were once stardust, hurled into space by these titanic stellar explosions? It's a humbling thought. The universe didn't just create the conditions for life, it literally handed us the tools to build it. This video is a journey back in time, to moments when dying stars lit up the darkness with the seeds of biology. We'll trace the path from these violent cosmic births to the delicate chemistry of life, uncovering how astrobiology and supernova are intertwined in ways that still leave scientists awestruck. So how did the chaos of a supernova give rise to the order of living cells? Why do these explosions hold the key to understanding our place in the cosmos? The answers lie in the forgotten link between the unimaginable power of dying stars and the fragile beauty of life. From the dust of stellar graveyards to the first stirrings of biology on distant worlds, we're about to explore a mystery that stretches across billions of years, one that connects every one of us to the farthest reaches of space. This is more than a story of atoms and explosions. It's the story of how the universe, in its infinite creativity, found a way to turn destruction into creation, and in doing so, made our existence possible. Buckle up, the cosmos has a tale to tell. To understand just how vital supernova are to life, we need to peer into the heart of these explosions where ordinary physics bends under forces so extreme they defy imagination. Inside a dying star, temperatures soar to billions of degrees, and pressures become so intense that atoms aren't just smashed together, they're completely rewritten. Hydrogen and helium, the simplest building blocks of the early universe, get crushed into heavier elements like carbon, the backbone of all organic chemistry. Oxygen, essential for respiration, gets forged in the same inferno. Even iron, the element that carries life giving oxygen through your bloodstream, is born in these violent final moments. But here's where it gets truly astonishing. Supernova don't just create these elements, they launch them into the void at nearly a tenth the speed of light, seeding entire galaxies with the ingredients for future worlds. Think of it like a cosmic bakery. A star spends its life slowly mixing simple ingredients, hydrogen and helium, like a patient chef preparing dough. But when it explodes, that kitchen transforms into a blast furnace, churning out everything from the salt in your tears to the phosphorus in your DNA. Without these explosions, the universe would be a sparse, lifeless place, just primordial hydrogen and helium drifting endlessly in the dark. Instead, supernova act as celestial recyclers, turning the ashes of dead stars into the raw materials for new solar systems. And the evidence is all around us. Meteorites, those ancient space rocks that occasionally fall to Earth, contain traces of elements like nickel-60, an isotope that can only form in the heart of a supernova. These tiny fragments are like cosmic time capsules, proving that our solar system, and by extension our bodies, are made from stardust forged in these titanic explosions. Even the gold in your jewelry or the uranium powering nuclear reactors owe their existence to supernova. Every heavy element, every mineral, every molecule that makes Earth habitable was once part of a star's dying breath. But the story doesn't end there. These newly minted elements don't just float aimlessly through space. They gather in vast clouds, drawn together by gravity over millions of years, until one day, a new star ignites, a star like our Sun, surrounded by planets built from the remnants of those ancient explosions. It's a cycle as old as the universe itself, destruction giving way to creation, chaos birthing complexity. And somewhere in that cosmic dance, on a small rocky planet orbiting an unremarkable star, those scattered atoms finally came together in just the right way to spark something extraordinary: life. The journey from stardust to DNA is one of the universe's most extraordinary transformations, a process that turns the ashes of dead stars into the blueprints of life itself. After a supernova scatters its elemental treasure across space, these atoms don't just drift aimlessly. They gather in vast, swirling clouds of gas and dust, cosmic nurseries where gravity works its slow magic. Over millions of years, these clouds collapse, heating up until new stars ignite at their cores. Around these stars, leftover material clumps together, forming planets, asteroids, and comets, each one a repository of those ancient stellar ingredients. Imagine a single atom of carbon forged in the heart of a dying star billions of years ago. After being blasted into space, it finds itself in a molecular cloud, then gets pulled into the disk of a young solar system. That carbon atom might end up trapped in a speck of dust that becomes part of a comet, which later crashes into a fledgling Earth. Here, it joins a dance of chemistry, perhaps bonding with oxygen to form carbon dioxide, or linking with hydrogen to create methane. But in the right conditions, surrounded by water and bathed in energy from lightning or sunlight, that same carbon atom could become part of something far more complex: a sugar molecule, an amino acid, or even a nucleotide, the building block of DNA. Scientists have found stunning evidence of this cosmic journey right here on Earth. Meteorites, particularly a rare type called carbonaceous chondrites, contain amino acids, the very molecules that form proteins in living cells. These space rocks are like frozen snapshots of the early solar system, proving that the ingredients for life were delivered to our planet from the stars. Even more remarkably, researchers have detected ribose, the sugar backbone of RNA, in meteorites, suggesting that the universe doesn't just provide raw materials, it might also hand us the tools to assemble them. But how do these simple molecules become the intricate structures of life? The answer lies in Earth's ancient oceans, where supernova-born elements mixed in a primordial soup. Near hydrothermal vents or in tidal pools, bathed in ultraviolet light or volcanic heat, these molecules began linking together, forming chains and complex structures. Over time, through countless chemical reactions and sheer cosmic luck, they gave rise to the first self-replicating molecules precursors to DNA. Every strand of DNA in your cells contains atoms that once resided inside a star, a direct line connecting you to the fiery deaths of distant suns. This isn't just poetic speculation. Modern telescopes have spotted organic molecules in the gas clouds around young stars, and lab experiments have shown how simple chemicals in space can evolve into complex ones under the right conditions. The universe, it seems, is hardwired to create the building blocks of life. From the chaos of a supernova to the delicate double helix of DNA, The cosmos has been weaving this story for billions of years, and we are its living, breathing proof. The universe is a delicate balancing act, too much chaos, and life never gets a chance to take root, too little, and the essential ingredients for biology remain locked away in the hearts of stars. This cosmic tightrope walk is what scientists call the astrobiological Goldilocks zone, the perfect middle ground where supernovae provide just enough heavy elements to build life without wiping it out before it begins. Picture our own galactic neighborhood. The Milky Way's spiral arms are dotted with stars, but not all of them are equally suited for nurturing planets like Earth. Too close to the galaxy's crowded center, and the frequency of supernova would bathe fledgling worlds in deadly radiation, shredding any fragile chemistry that might lead to life. Too far out in the sparse galactic outskirts, and there simply wouldn't be enough heavy elements to form rocky planets, let alone the complex molecules that make biology possible. What makes this balance so fascinating is the way it shapes the very architecture of life-friendly solar systems. Take iron, for example, a crucial element for everything from hemoglobin in your blood to the enzymes that power your cells. Without supernova, iron wouldn't exist in sufficient quantities to support advanced life. But if a supernova occurs too close to a young planetary system, the same iron atoms could arrive as part of a lethal wave of radiation, sterilizing the surface of any budding Earth-like world. It's like walking a knife's edge between abundance and annihilation, where the difference between a lifeless void and a thriving biosphere comes down to distance, timing, and sheer cosmic luck. Astrobiologists have even mapped these Goldilocks zones within our galaxy, identifying regions where the rate of supernova is neither too high nor too low. Our solar system, as it turns out, sits in one of these privileged pockets far enough from the galactic center to avoid constant bombardment, yet close enough to have inherited a rich supply of life-building elements from earlier generations of stars. This rare positioning might explain why Earth became such a fertile ground for life while other worlds, despite having water or organic molecules, remain barren. The implications for the search for extraterrestrial life are profound. When scientists scan distant exoplanets for signs of biology, they're not just looking for water or atmospheres, they're also considering the broader galactic environment. A planet orbiting a star in one of these astrobiological sweet spots instantly becomes a more promising candidate because it's more likely to have the right mix of elements and the right level of cosmic calm to nurture life over billions of years. It's a reminder that life isn't just a planetary phenomenon, it's a galactic one shaped by forces that stretch across light years and epochs. And here's the most humbling thought of all. If supernova had been just a little more frequent or a little more sparse, the delicate chain of events that led to our existence might never have happened. The atoms in your body, the planet beneath your feet, even the air you breathe, they're all products of a universe that somehow got the recipe just right. In the grand cosmic kitchen, supernova are both the chefs and the destroyers, and life exists in the fleeting moment where their fiery chaos yields to perfect order. The Crab Nebula, that ghostly tapestry of light in the constellation Taurus, isn't just a celestial spectacle, it's a time machine. When Chinese astronomers recorded its sudden appearance in the year 1054, they had no idea they were witnessing the aftermath of a supernova whose echoes would ripple across millennia. Today, that same remnant serves as a cosmic laboratory, revealing how the shattered remains of a star can seed the galaxy with the very elements that make life possible. Within its swirling filaments, telescopes detect oxygen, carbon, and neon elements flung outward at millions of kilometers per hour, now suspended in space like ingredients waiting to be stirred into future worlds. What makes these remnants so invaluable is their ability to freeze a moment in time. Unlike the fleeting brilliance of the explosion itself, supernova remnants linger for tens of thousands of years, allowing scientists to dissect their chemistry with extraordinary precision. Take Cassiopeia A, another stellar corpse roughly 11,000 light-years away. By analyzing the light from its expanding debris cloud, astronomers have mapped pockets of silicon next to veins of iron, physical proof of how a dying star's layered interior gets scrambled and ejected during the blast. These aren't just random scatterings, they're the fingerprints of nuclear reactions that occurred in the star's final seconds, a recipe book for how the universe cooks up heavy elements. But the real magic happens when these remnants interact with their surroundings. As the shockwave from a supernova plows through interstellar space, it rams into nearby gas clouds, compressing them and triggering new waves of star formation. This cosmic domino effect means that the same explosion that destroys a star can also ignite the birth of others along with their planetary systems. The famous pillars of creation in the Eagle Nebula, for instance, might owe their existence to a long-ago supernova shockwave, which sculpted those towering columns of gas and dust where new stars now flicker to life. Perhaps the most profound revelation comes from isotopic ratios, the subtle variations in elements, atomic structures that act like cosmic barcodes. In meteorites, scientists have found traces of nickel-60, a radioactive isotope that only forms in supernova. Its presence in our solar system's oldest rocks is like finding a grain of sand from a distant beach, proof that debris from a stellar explosion mingled with the cloud that birthed our sun and planets. Even more astonishing, some models suggest our solar system might owe its existence to not one, but multiple supernova, each contributing different layers of elemental richness like successive waves of cosmic seasoning. These remnants also solve a puzzle: how elements travel from their violent births to the calm environments where life can take root. Supernova don't just eject material, they propel it with enough force to penetrate molecular clouds, ensuring that heavy elements don't linger in sterile voids, but instead reach the stellar nurseries where rocky planets form. The Crab Nebula's filaments, for example, are laced with dust grains that will one day become part of future asteroids, comets, and perhaps even alien oceans. It's a reminder that the universe doesn't waste its creations. Every atom forged in chaos eventually finds its way into new stories, some of which, against all odds, include us. Yet for all their destructive power, supernova remnants are surprisingly delicate architects. Their expanding shells create vast, bubble-like structures in the galaxy, carving out cavities where elements can mix and react. In the Orion Nebula, just 1,500 light-years away, telescopes have spotted organic molecules like methanol and formaldehyde clinging to dust grains within such bubbles, molecules that could eventually become part of amino acids or sugars. This is the universe's grand recycling program: death feeding birth, destruction enabling creation, all on a scale so vast it humbles the imagination. So the next time you gaze at a supernova remnant in a telescope image, remember, you're not just looking at the aftermath of a star's death. You're seeing a cosmic delivery system, a celestial-fed X-truck hurtling through the galaxy with a payload of life's raw materials. And somewhere in that swirling debris, there might be atoms destined for a planet that doesn't even exist yet, waiting to spark another chapter in the universe's endless story of reinvention. While supernova are the universe's primary element factories, there's another cosmic event that specializes in crafting the rarest ingredients: neutron-star collisions, known as kilonovae. Imagine two city-sized stellar corpses, each so dense that a teaspoon of their material would weigh 1 billion tons, locked in a deadly spiral. When they finally collide, the impact unleashes a firestorm of nuclear physics, forging elements like gold, platinum, and uranium in quantities even supernova can't match. These explosions are so powerful they briefly outshine entire galaxies, and yet they're vanishingly rare. Only a handful occur in a galaxy like ours each million years. What makes kilonovae so special is their precision. Unlike the brute force chaos of a supernova, these collisions act like cosmic alchemists, carefully assembling atomic nuclei under conditions so extreme they defy earthly laboratories. In the merger's aftermath, neutron-rich material gets flung outward at relativistic speeds, forming a hot, expanding cloud where rapid neutron capture, a process called the R process, transforms ordinary atoms into heavyweights like gold and platinum. A single kilonova can produce hundreds of Earth masses worth of these precious metals, scattering them across interstellar space like seeds for future solar systems. The proof lies in our own planet's crust. The gold in your ring or the platinum in a catalytic converter didn't originate in Earth's molten interior. It arrived here via meteorites carrying remnants of ancient neutron star collisions. Even more telling, the relative abundance of these rare elements in our solar system matches computer simulations of kilonovae ejecta, a smoking gun linking these cosmic crashes to the chemistry of life. Without them, the periodic table would be missing some of its most fascinating entries, and Earth's geology, and by extension, human technology, would look radically different. But kilonovae's role extends beyond bling. Elements like iodine, essential for thyroid function, and thorium, used in advanced medical imaging, owe their cosmic origins to these mergers. Even more critically, the uranium that powers nuclear reactors and once fueled Earth's internal heat engine, driving plate tectonics, was likely forged in the aftermath of neutron star collisions. This means the very stability of our planet's geology, the slow churn of continents that recycles nutrients and regulates climate, might trace back to these cataclysmic events. The discovery of kilonovae has reshaped our understanding of cosmic chemistry. In 2017, astronomers witnessed history when gravitational wave detectors picked up the ripple from a neutron star collision while telescopes caught the accompanying fireworks show. The data revealed telltale signatures of heavy elements forming in real time, confirming what theorists had long suspected: kilonovae are the universe's exclusive workshops for the heaviest elements. This single observation, nicknamed GW170817, revolutionized astrobiology by proving that life's building blocks come from not one, but multiple cosmic crucibles. Yet for all their destructive beauty, kilonovae are picky about their real estate. They tend to occur in regions where earlier generations of stars have already seeded the galaxy with lighter elements, areas where supernova have already laid the groundwork. This creates a cosmic assembly line. Supernova provide the bulk materials like carbon and oxygen, while kilonovae add the finishing touches, the rare elements that add complexity to chemistry and enable advanced biology. Together, they weave a tapestry of elemental diversity that makes life as we know it possible, a collaboration spanning stellar lifetimes and galactic distances. So the next time you marvel at a sunset's gold-tinged light or rely on a platinum-coated medical implant, remember, you're touching relics of the universe's most exclusive fireworks. In a cosmos where even destruction serves creation, kilonovae remind us that rarity has value and that the most fleeting events can leave the most enduring legacies. The leap from stardust to the first stirrings of life is one of the universe's most astonishing transformations, a journey that turns scattered atoms into the intricate chemistry of biology. After supernova and kilonovae filled the cosmos with life's raw ingredients, those elements needed a stage where they could perform their magic. Enter Earth 4.5 billion years ago, a violent, molten world bombarded by asteroids and comets, its atmosphere thick with volcanic gases. It might seem like the last place you'd expect delicate organic molecules to survive, let alone thrive. Yet hidden in this chaos were the perfect conditions for probiotic chemistry, the cosmic cookbook that turned simple elements into the precursors of life. Picture a young Earth, its oceans still steaming from formation, as a hail of carbon-rich meteorites streaks through the atmosphere. These space rocks, remnants of the solar system's birth, carry more than just metals and minerals. Locked inside them are amino acids, sugars, and even nucleobases, the very letters of life's genetic alphabet. When they crash into warm tidal pools or hydrothermal vents, their payload dissolves into the water, creating a rich broth of organic material. Meanwhile, lightning crackles through the methane-laden air, ultraviolet light bathes the surface, and volcanic heat churns the depths. Each of these energy sources acts like a chef's torch, sparking reactions that link simple molecules into chains, forming proteins, fats, and other complex structures. Scientists have recreated these primordial conditions in labs with astonishing results. The famous Miller-Urey experiment in 1953 showed that a mix of water, methane, ammonia, and hydrogen gases thought to mimic Earth's early atmosphere could produce amino acids when zapped with electrical sparks. But the real breakthrough came decades later, when researchers discovered that meteorites contain even more diverse organic molecules than those created in the lab. Some carbonaceous chondrites, like the Murchison meteorite that fell in Australia in 1969, harbor over 90 different amino acids, including many not used by life on Earth. This suggests the universe isn't just providing ingredients, it's offering an entire menu of chemical possibilities. Yet the story doesn't end there. Recent experiments reveal that minerals found near hydrothermal vents can act as molecular factories, assembling amino acids into proteins or guiding the formation of RNA-like molecules. Clay surfaces, for instance, have charged edges that attract and align nucleotides, potentially helping them link into chains. Even the icy grains in comets, when exposed to starlight, can form complex organics. This means the building blocks of life might have arrived ready-made from space, then found Earth's dynamic environment ideal for further assembly. It's a cosmic collaboration. Supernovae provide the elements, asteroids deliver the starter kit, and Earth's geology and climate refine the recipe. The most tantalizing clue lies in ribose, the sugar backbone of RNA, detected in meteorites. RNA is often called the original molecule of life because it can both store genetic information and catalyze reactions, a dual role DNA can't match. Finding its components in space suggests the universe might favor certain molecular blueprints, nudging chemistry toward complexity. Add to this the discovery of phosphates essential for energy-carrying molecules like ATP in comet dust, and the pieces start falling into place. From the depths of space to the shores of ancient Earth, the universe seems hell-bent on creating the conditions for life, one chemical reaction at a time. But here's the twist: probiotic chemistry isn't unique to our planet. The same processes likely play out on countless worlds, wherever asteroids deliver organic material and energy sources drive reactions. Telescopes have spotted sugar molecules in interstellar gas clouds, while Mars rovers have detected organic compounds in the red planet's soil. Even Saturn's moon Enceladus, with its subsurface ocean and hydrothermal vents, could be running the same experiments Earth did billions of years ago. This universality hints that life might not be a fluke, but an inevitable outcome of cosmic chemistry, a whisper of order emerging from chaos, written in the language of supernova and sculpted by the laws of physics. So the next time you marvel at the complexity of a single cell, remember, its story began in the hearts of dying stars, was written in the icy depths of space, and found its voice on a young, turbulent Earth. The universe didn't just create life, it set the table, prepared the ingredients, and then waited patiently for the right moment to serve the meal. And we, along with every living thing on this planet, are the lucky guests at that cosmic banquet. The universe has been quietly assembling life's ingredients for billions of years, and the proof is falling from the sky. Meteorites, those ancient fragments of asteroids and comets, are more than just space rocks. They're treasure chests packed with organic molecules. Take the Murchison meteorite, which landed in Australia in 1969. Inside its charcoal-colored exterior, scientists discovered over 90 different amino acids, the same molecular building blocks that form proteins in every living organism on Earth. What's astonishing isn't just their presence, but their diversity. Many of these amino acids don't even exist in terrestrial biology, proving they weren't contaminants but genuine extraterrestrial arrivals. These molecules didn't form in Earth's oceans or forests. They were crafted in the cold depths of space, likely within the icy mantles of dust grains that swirled around newborn stars. But how do delicate organic compounds survive the brutal conditions of space? The answer lies in cosmic chemistry's quiet efficiency. Far from the violent chaos of supernova, in the frigid clouds between stars, simple molecules like water, ammonia, and methanol freeze onto microscopic dust grains. They're shielded from harsh radiation. They undergo slow-motion reactions, a kind of interstellar slow cooker. Ultraviolet light or cosmic rays provide just enough energy to nudge these molecules into more complex forms, including amino acids and even the nucleobases that make up DNA. It's a process so widespread that the Atacama Large Millimeter Array in Chile has detected sugar molecules floating in the gas clouds around young stars, while infrared telescopes have spotted the chemical fingerprints of alcohols and ethers in distant nebulae. The real game-changer came when scientists found ribose, the sugar backbone of RNA in meteorites like the 2012 Sutter's Mill specimen. RNA is often called the original molecule of life because it can both store genetic information and catalyze chemical reactions, making it a prime candidate for Earth's first self-replicating molecule. Finding its components in space suggests the universe doesn't just provide raw materials, it might also hand-deliver the instruction manual. Even more compelling, some meteorites contain molecules like quinons, which are crucial for electron transfer in cellular respiration, and phospholipids, the building blocks of cell membranes. It's as if the cosmos pre-packaged a starter kit for biology. What ties these discoveries back to supernova is their isotopic signatures. Many meteoritic organics contain unusual ratios of nitrogen-15 to nitrogen-14, or carbon-13 to carbon-12 ratios that match predictions for chemistry occurring in the aftermath of stellar explosions. When a supernova shockwave slams into a molecular cloud, it doesn't just deliver heavy elements, it also triggers cascades of organic synthesis. Laboratory experiments have shown that icy mixtures bombarded by simulated supernova shockwaves can produce amino acids in minutes, suggesting these cosmic cataclysms might act as both destroyers and creators, shattering stars while jump-starting the chemistry of life. The implications for astrobiology are staggering. If organic molecules are this abundant in our own solar system's debris, imagine how many might be drifting around younger, more metal-rich star systems. The Rosetta mission's discovery of glycine, the simplest amino acid in the coma of comet 67P Churyumov-Gerasimenko, confirmed that these compounds can survive the journey from interstellar space to planetary surfaces. Europa's subsurface ocean or Titan's methane lakes might be simmering with similar chemistry right now, fed by cometary deliveries over billions of years. This isn't just about Earth's history, it's a window into life's cosmic potential. The same processes that filled our planet's primordial pantry could be operating right now around Proxima Centauri or TRAPPIST-1, turning sterile worlds into future incubators of biology. Every meteorite that lands on Earth is a messenger from that grander story, whispering that life's ingredients aren't rare flukes, but inevitable products of a universe that seems hardwired for complexity. And if supernova are the furnaces forging those ingredients, then every exploding star might be, in its own violent way, sowing the seeds for life across the galaxy. The silence of the cosmos might not be a sign that life is rare, but rather that the universe is a far more dangerous place than we realize. The Fermi Paradox, which asks why we haven't found evidence of alien civilizations despite the vast number of stars, takes on a chilling new dimension when we consider the role of supernova. These explosions don't just create the building blocks of life, they might also act as cosmic reset buttons, wiping out fledgling civilizations before they ever get the chance to reach the stars. Imagine a planet like Earth orbiting a star in one of the Milky Way's spiral arms. Over billions of years, life emerges, evolves, and perhaps even develops intelligence. But just as that civilization begins to explore beyond its home world, a nearby star explodes, a supernova so close that its gamma-ray burst sterilizes the planet, stripping away atmospheres and boiling oceans in an instant. The very same forces that delivered the elements for life now snuff it out, leaving behind a radioactive wasteland. This scenario isn't science fiction, it's a real possibility supported by geological evidence. Layers of iron-60 isotopes in Earth's seafloor suggest our planet was bathed in radioactive debris from a supernova as recently as 2.6 million years ago, coinciding with a mass extinction event. The implications are staggering. Regions of the galaxy with higher supernova rates could be caught in a cycle of creation and destruction, where life arises only to be erased before it can spread. Our solar system's location, far enough from the crowded galactic center, but still enriched with heavy elements, might be a rare sweet spot where civilizations can develop without constant cosmic interference. Even more sobering, some researchers suggest that intelligent life might need to emerge during a narrow window of galactic quietude, after the worst of the early universe's bombardment, but before wandering stars or black holes drift too close. But the paradox deepens when we consider time. Supernovae aren't evenly distributed across the galaxy's history. They were far more frequent in the Milky Way's youth. Early civilizations, if they existed, would have faced even deadlier odds. This raises a haunting question. Could we be among the first life forms to reach this level of complexity simply because the universe is only now becoming survivable? The same stellar furnaces that forged our atoms might have kept the cosmos silent for billions of years, making humanity not late to the party, but surprisingly early. Yet there's another twist. Supernova might not just be destroyers, they could also be unintentional guardians. Some models suggest that gamma-ray bursts, while deadly to nearby systems, might carve out safe zones in their aftermath, clearing space of potential threats and allowing life to flourish in their wake. It's a cosmic irony. The same explosions that erase civilizations could also create the conditions for their eventual rise. So when we peer into the night sky and wonder where everyone is, the answer might be written in the fading light of ancient supernova. The universe isn't just a stage for life, it's a battlefield where the same forces that give rise to biology can also tear it down. The silence isn't emptiness, it's the echo of countless resets, a reminder that existence is as fragile as it is extraordinary. And if we're here today, it's not just because the cosmos built us, it's because against all odds, it let us survive. Long before telescopes or spectrometers, humans looked to the night sky and saw something impossible, a star where none had been before, blazing brighter than Venus, outshining the moon. These sudden apparitions, now known as supernova, weren't just celestial oddities to our ancestors. They were messages, omens, and cosmic turning points etched into the very fabric of human culture. Take the supernova of 1054, recorded by Chinese astronomers as a guest star, so luminous it was visible in daylight for 23 days. To the Song dynasty court, it signaled divine approval for a new emperor, while half a world away, ancestral Puebloans may have painted its likeness onto canyon walls in present-day Arizona. These weren't just observations, they were dialogues with the universe, attempts to reconcile the heavens' sudden violence with life on Earth. The Crab Nebula's progenitor star didn't just leave behind a glowing remnant, it left fingerprints on human history. In Japan, the same supernova was linked to the legend of Terra no Masakoto, a rebellious samurai whose restless spirit was said to flare alongside the new star. Half a millennium earlier, the supernova of 185, documented by Han Dynasty astronomers as a broom star, coincided with the downfall of Emperor Ling's corrupt regime, reinforcing the ancient Chinese belief that celestial disruptions mirrored earthly turmoil. Even the Bible's book of Revelation contains tantalizing hints. Some scholars suggest the star called wormwood that falls from heaven, turning waters bitter, could describe a supernova's aftermath visible to Mediterranean cultures. But the connections run deeper than records and legends. The Aboriginal Australians' emu in the sky, a dark dust cloud silhouette against the Milky Way, may encode memories of supernova in its shifting orientation across generations. Norse mythology's Ragnarök, with its fiery sky and collapsing world tree, bears uncanny resemblance to a supernova's light echoing through oral traditions. These weren't primitive fantasies, they were sophisticated attempts to process cosmic trauma, to weave stellar explosions into cultural narratives that gave meaning to the inexplicable. What's striking is how consistently these events became linked to transformation, whether as harbingers of doom in European astrology or as celestial rebirth symbols in Mesoamerican codices. Supernova served as punctuation marks in humanity's story, moments when the universe seemed to speak directly to civilization. The Tycho supernova of 1572, observed by the Danish astronomer whose name it bears, wasn't just a scientific milestone, it shattered Aristotle's doctrine of an unchanging heavens, paving the way for the scientific revolution. In that single burst of light, medieval cosmology collapsed and modern astronomy began. Today, we understand these events as natural phenomena, yet their cultural legacy lingers. The very word disaster comes from the Latin for bad star, a linguistic fossil of our ancestors' belief that celestial and earthly fates were intertwined. From Shakespeare's portentous comets to modern sci-fi's supernova metaphors for societal collapse, these stellar explosions remain embedded in our collective psyche, not just as astrophysical events, but as mirrors reflecting humanity's eternal quest to find meaning in the cosmos. The stars that died to make our atoms also shaped our stories, proving that culture and chemistry share the same stellar ancestry. Modern telescopes have transformed supernova from distant flashes into open books, their pages filled with the universe's elemental recipes. Take the James Webb Space Telescope. Its infrared eyes peer through cosmic dust, capturing the chemical fingerprints of dying stars with precision once unimaginable. When JWST observed the remnants of Cassiopeia A, it didn't just see a shattered star, it mapped swirling tendrils of silicon and iron, tracing how these elements mix in the aftermath of catastrophe. Hubble, with decades of service, has chronicled supernova fading over months, their light curves acting as cosmic barcodes that reveal the exact type and energy of each explosion. Together, these instruments form a time machine, showing us not just what supernova are today, but what they meant for galaxy evolution billions of years ago. The real breakthrough lies in spectroscopy, splitting starlight into rainbows that betray the presence of specific elements. When a supernova's light passes through JWST instruments, dark lines appear in its spectrum like missing puzzle pieces, each corresponding to oxygen, carbon, or neon. By comparing these patterns across different galaxies, astronomers have uncovered a startling truth. Supernova don't distribute their elements evenly. Spiral arms, where stars form most vigorously, show higher concentrations of life-critical elements like phosphorus, while galactic outskirts remain relatively barren. This patchwork distribution means the potential for life isn't just about having a rocky planet, it's about being in the right stellar neighborhood at the right cosmic moment. Recent observations have also appended assumptions about supernova diversity. The Zwicky Transient Facility, scanning the entire northern sky every 2 nights, has caught supernova erupting in unexpected environments like dwarf galaxies with chemical compositions resembling the early universe. These explosions produce element mixes distinct from those in metal-rich galaxies, offering clues about how the first heavy elements spread through pristine cosmic landscapes. Meanwhile, gravitational wave detectors like LIGO have begun pairing with telescopes to catch kilonovae neutron star collisions that forge gold and platinum in real time, creating multi-messenger astronomy's most thrilling chapters. But perhaps the most profound discoveries come from supernova's role in cosmic recycling. ALMA, the radio telescope array in Chile, has spotted molecules like aluminum monoxide in supernova debris, proof that even in destruction, chemistry persists. These molecules eventually cling to dust grains, which drift into molecular clouds to become part of new planetary systems. It's a process now observable in stunning detail. Hubble's images of the Cygnus loop show shockwaves compressing interstellar gas, triggering molecule formation amid the chaos. This means every water molecule on Earth might trace back not just to stardust, but to the turbulent aftermath of specific explosions that occurred before our sun even ignited. The data deluge from these telescopes has spawned an unexpected tool: machine learning. Algorithms sift through millions of galaxy images to spot supernova within hours of eruption, sometimes before human observers notice. One such program at the Pan-STARRS Observatory in Hawaii identified a supernova whose light contained unusual uranium signatures, hinting at rare hypernova events that might dominate the early universe's element production. These AI assistants are rewriting textbooks, revealing that supernova come in far more varieties than the classic types Ia and Roman II, each with its own elemental contribution to life's recipe. What emerges from this observational revolution is a humbling realization. We're not just studying supernova, we're auditing our own cosmic inheritance. When JWST detects organic molecules in a supernova's debris field, or when Hubble catches a shockwave enriching a nearby nebula, we're witnessing steps in a chain that leads directly to the chemistry of our bodies. These telescopes aren't merely instruments, they're mirrors reflecting our deepest origins, showing us that the line between stellar death and biological birth is far thinner than we ever dreamed. As we stand on the brink of discovering thousands of new exoplanets, the legacy of supernova takes on urgent new meaning. The next generation of telescopes, like the Habitable Worlds Observatory currently in development, won't just scan distant planets for water or oxygen. They'll hunt for the subtle chemical fingerprints of stellar explosions, clues revealing whether a world inherited the right mix of elements to nurture life. Imagine analyzing the atmosphere of an Earth-like planet 40 light-years away and detecting unusual ratios of potassium to iron, a telltale sign that its solar system formed from the ashes of a particular type of supernova. This isn't science fiction. It's the cutting edge of astrobiology, where the violent deaths of stars become roadmaps to finding life. The key lies in understanding how supernova act as cosmic architects, shaping not just individual planets but entire galactic habitable zones. Take the TRAPPIST-1 system with its 7 rocky worlds orbiting a cool dwarf star. 3 of these planets sit in the so-called Goldilocks zone, but whether they could actually support life depends heavily on their primordial chemistry. If a nearby supernova enriched their birth cloud with too little phosphorus, a critical element for energy storage in cells, or too much radioactive aluminum, their potential for biology might have been doomed from the start. Future missions like ESA's Ariel spacecraft will analyze exoplanet atmospheres for such elemental imbalances, effectively reading the stellar ancestry of distant worlds. But the real revolution comes when we combine these observations with advanced modeling. Astrophysicists now run simulations tracking how supernova debris migrates through galaxies over billions of years, revealing unexpected patterns. Some computer models suggest that certain types of supernova create elemental highways, concentrated streams of life-building materials that flow along spiral arms. Planets forming near these cosmic rivers might receive richer deliveries of carbon or nitrogen than their neighbors just a few light-years away. This could explain why, even within a single star system, some worlds become fertile while others remain barren. The implications for the search for extraterrestrial life are profound. Instead of just looking for planets with liquid water, astrobiologists are beginning to consider supernova enrichment scores, metrics that quantify how well a world was seeded with the right elements in the right proportions. The Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, a proposed NASA flagship mission, could one day map these elemental distributions across thousands of star systems, identifying which ones had the best cosmic head start. Perhaps most intriguing is how this perspective flips the script on rare Earth hypotheses. If supernova are the universe's primary chemists, then planets with the right elemental recipe might be more common than we thought, but only in specific galactic neighborhoods. The challenge becomes finding those Goldilocks regions where supernova occurred frequently enough to deliver life's ingredients, but not so often that they sterilize budding biospheres with radiation. It's a delicate balance, one that turns every new exoplanet discovery into a cosmic detective story, tracing its elemental lineage back to the stars that died to make it. This approach also reshapes how we interpret potential biosignatures. Phosphine gas detected in a distant atmosphere might hint at life, but first we'd need to rule out that it wasn't simply inherited from a phosphorus-rich supernova event. Similarly, oxygen could accumulate abiotically on worlds bathed in certain types of stellar debris, creating false positives in our search for alien biospheres. The next frontier in astrobiology isn't just about finding the right conditions for life. It's about unraveling whether those conditions were forged by biology or by the ancient explosions of massive stars. As we prepare to launch these revolutionary telescopes, we're not just building better instruments. We're learning to read the universe's grand narrative, one where the death throes of stars write the opening chapters of life's story. And with each new discovery, we come closer to answering humanity's oldest question. In a cosmos shaped by supernova, are we alone or just one thread in a vast tapestry of living worlds? Inside a nondescript laboratory at the University of Chicago, scientists are recreating the most violent events in the universe on a tabletop. Using lasers powerful enough to vaporize steel, they compress samples of hydrogen and helium to pressures 1 billion times greater than Earth's atmosphere, mimicking the conditions inside a dying star. For a fraction of a second, atoms are crushed together with such force that they fuse into heavier elements: carbon, oxygen, and beyond. This isn't just about spectacle. It's a meticulous effort to decode the universe's most fundamental recipe: how supernova transforms stardust into the chemistry of life. These experiments reveal surprises that telescopes alone can't capture. When researchers at the National Ignition Facility blast tiny pellets of material with lasers, they observe how shockwaves ripple through stellar debris, creating pockets where exotic isotopes form. One startling discovery: the production of calcium vital for bones and teeth spikes under conditions simulating certain types of supernova. This helps explain why calcium is so abundant in our solar system compared to predictions from stellar models. Similarly, lab simulations of neutron star collisions show how gold and platinum nucleate in neutron-rich environments, solving a decades-old puzzle about why these metals cluster in certain meteorites. But the real magic happens when scientists go beyond element creation to study how these atoms interact. At NASA Ames Research Center, astrophysicists recreate the frigid vacuum of interstellar space, bombarding ice-coated dust grains with radiation to simulate a supernova's aftermath. Within days, simple ices transform into complex organics: amino acids, sugars, even components of DNA. The key finding: supernova shockwaves don't just deliver elements, they provide the energy to jumpstart prebiotic chemistry. This means the same explosion that forges iron might also spark the formation of molecules essential for life. One groundbreaking experiment in Germany took this further by simulating how supernova-generated elements could catalyze reactions on early Earth. When researchers mixed synthetic meteorites containing supernova-synthesized nickel with warm water and carbon dioxide, mimicking primordial oceans, they observed the spontaneous formation of acetic acid, a precursor to metabolism. This suggests that stardust didn't just arrive on our planet passively. It carried chemical blueprints for self-organization. The implications stretch far beyond our origins. By tweaking lab conditions to match exoplanet environments, say, higher silicon ratios or lower oxygen levels, scientists can predict which alien worlds might have inherited the right elemental mix for biology. Already, experiments simulating high phosphorus supernova debris hint at why phosphorus, a rare but critical element for life, is curiously abundant on Earth. Similar work could reveal whether Europa's subsurface ocean or Titan's methane lakes received comparable stellar deliveries. What makes these lab simulations revolutionary is their ability to turn cosmic mysteries into testable science. Every laser pulse and chilled reaction chamber acts as a time machine, letting us witness events that shaped our existence but occurred light years away and billions of years ago. The data pouring from these experiments are rewriting textbooks, proving that life's building blocks aren't just products of chance, they're inevitable outcomes of physics playing out across the universe. And with each discovery, we're not just learning how stars die, we're uncovering the universal pathways that turn their ashes into the chemistry of life. The idea that the universe might be fine-tuned for life isn't just poetic speculation, it's a puzzle that has haunted physicists and philosophers for decades. Consider this: if the rate of supernova were even slightly higher, the galaxy would be bathed in lethal radiation, sterilizing planets before life could take hold. If it were lower, heavy elements like carbon and oxygen might never spread far enough to form rocky worlds. The balance is so precise that it borders on the uncanny, leading some to wonder, is this cosmic perfection just a staggering coincidence, or is there something deeper at play? This is the essence of the anthropic principle, the observation that the universe's fundamental constants appear meticulously calibrated to allow life's existence. Take gravity, for instance. If it were a fraction stronger, stars would burn out too quickly for life to evolve. A fraction weaker, and matter might never clump together to form stars at all. The same delicate dance applies to supernova. Their explosions must be powerful enough to forge and scatter heavy elements, but not so frequent that they obliterate nascent solar systems. Even the nuclear forces binding atoms together are exquisitely balanced. Tweak them slightly, and carbon, the backbone of life's chemistry, might never form in stellar cores. Critics argue this apparent fine-tuning is a trick of perspective. Of course, we observe a universe compatible with life because we couldn't exist in one that wasn't. But supporters counter that the odds against such perfect conditions arising by chance are astronomical. Some propose radical explanations, like the multiverse theory, where countless universes with different constants exist, and we simply inhabit the one where the numbers lined up just right. Others see it as evidence of deeper laws we've yet to uncover, or even, though more controversially, hints of intentional design. The debate takes on new urgency when we consider how rare our cosmic neighborhood might be. Simulations show that even in galaxies like ours, only certain regions far from deadly gamma-ray bursts, yet enriched with life's building blocks, offer stable enough environments for intelligent life to emerge. This cosmic real estate is vanishingly scarce, making Earth's existence feel less like luck and more like a statistical miracle. Whether you see this as profound or merely provocative, one thing is undeniable: the universe's recipe for life depends on a series of impossibly precise steps, each linked to the violent, beautiful deaths of stars. And that realization changes how we see our place in the cosmos, not as accidental guests, but as witnesses to a story written in the ashes of supernova. Supernova don't just shape the chemistry of life, they might also determine where intelligence can emerge in the cosmos. For decades, the search for extraterrestrial intelligence, or SETI, focused on scanning stars similar to our Sun, assuming they'd be the most likely hosts of advanced civilizations. But this approach overlooks a critical factor: the galactic environment itself. A planet might have all the right ingredients for life, but if it orbits in a region plagued by frequent supernova, any budding civilization could be erased by radiation long before it develops radio telescopes or spaceflight. This realization has led SETI researchers to rethink their strategy, turning their attention to what some call supernova-safe zones, regions where stellar explosions have enriched the galaxy with life's building blocks without sterilizing it too often. Take the Orion Spur, the minor spiral arm where our solar system resides. It's far enough from the crowded galactic center to avoid deadly gamma-ray bursts, yet close enough to have absorbed heavy elements from generations of supernova. This balance of enrichment and stability might be rare. Computer simulations suggest that less than 10% of stars in the Milky Way enjoy similar conditions. That means if intelligent life requires not just the right planet, but also the right galactic neighborhood, SETI search space could be far smaller than we imagined. The challenge lies in timing. Supernova aren't just spatial hazards, they're temporal ones. A civilization might arise during a quiet period, only to be wiped out when a nearby star explodes millions of years later. This adds a grim twist to the Fermi Paradox. The reason we haven't detected alien signals might not be because intelligence is rare, but because civilizations have narrow windows to survive between cosmic catastrophes. Some researchers now model galactic habitability timelines, mapping how often different regions experience life-friendly conditions. The results are sobering. Entire spiral arms might flicker between fertile and sterile states over cosmic timescales, leaving only fleeting opportunities for intelligence to flourish. Yet there's an optimistic angle to this. If civilizations know their window might be limited, they could prioritize broadcasting their existence early in their development. This might explain why some SETI initiatives like Breakthrough Listen are now targeting younger planetary systems, ones that recently entered stable periods between supernova events. The logic is simple. A civilization aware of its precarious cosmic real estate might shout into the void sooner rather than later, hoping to be heard before the next stellar explosion silences them. The search parameters are evolving beyond just star types. New telescopes like the Square Kilometer Array will scan not just for radio signals, but for chemical signatures of supernova-enriched systems. If a planet's atmosphere shows unusually high levels of elements like phosphorus or molybdenum, traces of specific supernova types, it could jump to the top of the target list. Similarly, projects like NASA's upcoming Habitable Worlds Observatory might prioritize scanning exoplanets with isotopic ratios matching Earth's, hinting they formed from similar stellar debris. This shift reflects a deeper truth. The story of intelligence in the universe isn't just about biology or technology, it's about surviving the cosmos itself. The same explosions that gave us the iron in our blood and the calcium in our bones could also be the universe's way of resetting the clock, ensuring that no civilization grows too dominant or lasts too long. Whether this makes the galaxy feel lonely or strangely balanced depends on perspective. But one thing is certain: if we ever do detect an alien signal, it won't just be a message from another world, it'll be a testament to life's resilience against the fiery chaos of the stars. The dream of interstellar travel brings with it a sobering reality. Supernova, the very events that forged life's building blocks, could also erase it in an instant. Picture a generation ship, centuries into its voyage to a distant star, suddenly bathed in lethal gamma rays from a stellar explosion just a few dozen light-years away. The same forces that seeded the galaxy with carbon and oxygen now threaten to sterilize any vessel caught in their deadly crossfire. This isn't speculative fiction. It's a concrete challenge future explorers must confront. While Earth's atmosphere and magnetic field shield us from all but the closest supernova, a spacecraft, or worse, a fledgling colony on an exoplanet would have no such protection. The irony is staggering. The elements that make life possible might also limit its spread across the cosmos. Mapping these cosmic danger zones has become a priority for agencies planning humanity's next great leap. Recent surveys by the Gaia spacecraft reveal our solar system is currently drifting through a relatively quiet bubble in the Orion Arm, with the nearest potential supernova candidate, Betelgeuse, comfortably distant at 640 light-years. But venture beyond this local safe zone and the risks multiply. The Crab Nebula, a stellar nursery 5 times closer than Betelgeuse, hosts dozens of massive stars destined to explode within the next million years, a blink in cosmic time. For colonies established in such regions, survival might depend on early warning systems detecting pre-supernova neutrino bursts, giving just enough time to take shelter underground or behind improvised radiation shields. The challenge isn't just avoiding active supernova, it's navigating their lingering aftermath. When a star explodes, it leaves behind an expanding bubble of radioactive debris that can persist for millennia. The local bubble, a cavity in interstellar space surrounding our solar system, was likely carved out by multiple supernovae between 10 and 20 million years ago. Its remnants still contain elevated levels of iron-60, a radioactive isotope with a half-life of 2.6 million years that's been found embedded in deep-sea sediments and lunar regolith. Future interstellar navigators might need to chart courses around these ancient blast zones, where cosmic rays are intensified like rapids in a river. What makes this dilemma so fascinating is how it mirrors Earth's own history. Geological evidence suggests supernovae have triggered mass extinctions before layers of iron-60 in ocean crust correlate with the Pliocene marine megafauna extinction 2.6 million years ago. If natural selection on Earth was shaped by these stellar cataclysms, perhaps the same pressures will apply to spacefaring civilizations, favoring those who develop robust shielding or the ability to predict stellar deaths with precision. Some theorists even propose that advanced alien civilizations might deliberately cluster in galactic regions with low supernova rates, creating invisible islands of stability in an otherwise hazardous cosmos. This intersection of astrobiology and practical spaceflight reveals a profound truth. The universe isn't just our birthplace, it's an obstacle course we must learn to navigate. Every decision about where and when to send missions will require weighing the promise of habitable worlds against the peril of stellar time bombs. The same telescopes that once helped us understand our cosmic origins may one day serve as early warning systems, their lenses trained not on distant galaxies, but on the unstable stars lining our path to the stars. In this light, supernovae become more than just celestial spectacles. They're the gatekeepers of the galaxy, reminding us that space was never meant to be conquered, only carefully, respectfully traversed. Supernovae have long been the ultimate cosmic spectacle in science fiction, serving as both dazzling backdrops and existential threats, from Arthur C. Clarke's The Star, where a supernova's light reveals an ancient civilization's tragic fate, to the apocalyptic visions of films like Sunshine. These stellar explosions embody humanity's awe and terror in the face of cosmic forces. What's fascinating isn't just their dramatic potential, it's how fictional portrayals often mirror real scientific debates. Take Star Trek Roman II, The Wrath of Khan, where the Genesis device uses a proto-matter formula to terraform planets, echoing actual theories about supernova debris seeding life. Even when Hollywood takes liberties like the instant kill supernova radiation in The Force Awakens, these stories reflect our subconscious understanding that stars hold the keys to both life and death. Dig deeper and you'll find sci-fi grappling with the same paradoxes that puzzle astrophysicists. Liu Cixin's The Three-Body Problem depicts a civilization fleeing their supernova-threatened system, a poignant metaphor for humanity's own precarious cosmic neighborhood. Meanwhile, Interstellar visualizes time dilation near a dying star, blending real relativity with emotional stakes. These narratives tap into a profound truth. Supernovae aren't just events, they're turning points in the universe's story, moments when destruction and creation collide. Yet fiction's greatest contribution might be how it reshapes public perception of science. When Cosmos paired Carl Sagan's "We Are Star Stuff" monologue with swirling supernova visuals, it transformed a complex astrophysical process into cultural shorthand for human connection to the cosmos. Video games like Mass Effect take it further, weaving supernova-derived Element Zero into their lore as a nod to real exotic matter theories. This feedback loop between science and storytelling keeps the wonder alive, inspiring new generations to study the stars while reminding us that every scientific fact was once someone's wildest imagination. What emerges is a cultural tapestry where supernovae symbolize more than physics. They're narrative fulcrums. In Doctor Who, a supernova's energy becomes a time travel fuel. In Hitchhiker's Guide, it's the punchline to a galactic bureaucracy joke. Whether as metaphors for rebirth or warnings of fragility, these portrayals reveal how deeply stellar death shapes our collective psyche. The next time you watch a supernova light up a movie screen, remember, you're not just seeing special effects. You're witnessing the latest chapter in an ancient dialogue between the stars and the stories we tell about them. It's easy to see why supernovae have a fearsome reputation after all. These explosions can outshine entire galaxies and unleash enough energy to vaporize nearby worlds. Hollywood loves portraying them as cosmic doomsday devices, while news headlines warn of nearby stars that might go supernova and wipe out life on Earth. But here's the twist: without these cataclysmic events, life as we know it wouldn't exist at all. The very atoms that make up our bodies, the air we breathe, and the ground beneath our feet were forged in the heart of dying stars and scattered across the cosmos by their violent deaths. This paradox that destruction and creation are two sides of the same cosmic coin is one of astrobiology's most profound revelations, yet it's rarely part of the mainstream conversation. Consider the way we talk about nuclear power. To some, it's synonymous with Chernobyl or Fukushima-controlled, terrifying energy. But that same process, when harnessed carefully, lights up cities and powers life-saving medical equipment. Supernovae operate on a similar duality. Yes, their immediate effects are devastating, but their long-term legacy is nothing short of miraculous. Take iron, for example. Every drop of blood in your body contains iron atoms that were once at the core of a massive star. When that star exploded, it didn't just obliterate itself, it launched those iron atoms into space, where they eventually became part of Earth's crust, then the soil, then the plants we eat, and finally the hemoglobin in our veins. The same explosion that could sterilize a planet is also the reason you can stand upright without collapsing. This misunderstanding extends to how we imagine the universe's timeline. Many people picture the cosmos as a static backdrop, with stars merely twinkling in place until they fade away. In reality, our galaxy is a dynamic ecosystem where stars live, die, and recycle their materials in an endless loop. Supernovae aren't anomalies, they're part of the universe's natural rhythm, like autumn leaves falling to nourish the soil for new growth. When a star explodes, it doesn't just vanish, it becomes the raw material for future stars, planets, and potentially life. The Crab Nebula, with its delicate filaments of glowing gas, isn't a graveyard, it's a nursery, scattering the elements that might one day form new worlds. Even the fear of a nearby supernova wiping out Earth deserves nuance. While it's true that a close-range gamma-ray burst could be catastrophic, the odds are astronomically low. The last supernova known to have affected Earth occurred roughly 2.6 million years ago, and even then, its impact was subtle, a slight increase in radiation that may have influenced cloud formation. Meanwhile, the benefits of supernova are constant and universal. Every time you take a breath, you're inhaling oxygen atoms that were created in a stellar explosion billions of years ago. Every time you admire a sunset's colors, you're seeing light scattered by nitrogen and other elements forged in supernova. The universe isn't just a dangerous place, it's a generous one, offering the ingredients for life with every catastrophic act of stellar recycling. Changing these misconceptions isn't just about correcting facts, it's about reshaping how we see our place in the cosmos. When we reduce supernova to mere explosions, we miss their true role as cosmic alchemists, turning simplicity into complexity, chaos into order. The next time you look up at the night sky, remember, Those distant points of light aren't just decorations. They're the factories, the recyclers, the architects of existence itself. And somewhere in their fiery hearts, they're cooking up the elements that will one day build new worlds, new life, and perhaps new minds to wonder at the stars. Knowing that we are literally made of stardust doesn't just change our scientific understanding, it rewires our sense of belonging in the cosmos. For centuries, humanity placed itself at the center of creation, separate from and above the natural world. But the revelation that our atoms were forged in the hearts of dying stars collapses that hierarchy. We aren't just observers of the universe, we're its direct offspring, woven from the same elemental fabric as galaxies and nebulae. This shifts the ethical lens dramatically. If Earth's biosphere is a continuation of stellar processes, then environmental stewardship isn't just about preserving resources. It's about honoring a cosmic inheritance billions of years in the making. Consider biodiversity through this stellar perspective. Every endangered species, from rainforest orchids to deep-sea microbes, carries atoms synthesized in supernova. Their extinction wouldn't just be a terrestrial loss, it would erase unique configurations of stardust that the universe spent eons assembling. Indigenous cosmologies often speak of this interconnectedness, like the Maori concept of Wakapapa, where all life shares a genealogical bond tracing back to the stars. Modern astrobiology arrives at a strikingly similar conclusion through science. When we clear-cut forests or pollute oceans, we're not merely disrupting ecosystems, we're dismantling cosmic artistry. This perspective also reshapes how we approach space exploration. The debate over mining asteroids or Mars often centers on economic potential, but what if we framed it as cosmic archaeology? Those metallic asteroids are fragments of primordial supernova, carrying chemical stories about our origins. Strip mining them without study could be like burning ancient manuscripts for kindling. Some ethicists argue for a prime directive, inspired by stellar heritage guidelines, ensuring we explore space as mindful participants rather than colonial extractors. After all, the same processes that built our solar system are unfolding right now around young stars. We're essentially time travelers encountering our own past in distant planetary nurseries. The philosophical implications run even deeper. If life emerges naturally from universal chemistry, as supernova evidence suggests, then intelligence might be the cosmos' way of comprehending itself. Your ability to ponder these words, to marvel at the night sky, that stardust becoming self-aware, this flips traditional narratives about humanity's insignificance in a vast universe. Rather than being inconsequential specks, we're the universe's rare opportunity to reflect on its own beauty and complexity. That realization carries profound responsibility. If we're the universe's eyes and ears, then how we treat each other and our planet isn't just personal or political, it's a cosmic act. Yet this view also raises unsettling questions. If life is inevitable where conditions allow, as supernova-enriched chemistry implies, why haven't we found other civilizations? The silence could suggest that intelligence frequently self-destructs, that technological advancement outpaces ethical maturity. Our nuclear weapons, climate crises, and AI dilemmas might be universal growing pains, filters many civilizations fail to pass. Viewed this way, survival isn't just pragmatic, it's a moral imperative to prove Stardust can evolve wisdom alongside knowledge. Perhaps most radically, this framework dissolves the boundary between spirituality and science. When a Buddhist monk speaks of interbeing or a physicist describes quantum entanglement, both point to a fundamental unity, the same unity implied by our shared stellar ancestry. This isn't about replacing telescopes with prayer beads, but recognizing that wonder and curiosity are themselves cosmic phenomena. Every time a child asks why the stars shine or a researcher devotes years to studying supernova remnants, they're participating in the universe's ongoing story of self-discovery. So where does this leave us? Not as accidental tourists in an indifferent universe, but as active participants in a grand, unfinished symphony of matter and energy. The carbon in your coffee, the oxygen in your lungs, the iron in your blood, these aren't just resources or biological trivia. They're invitations to live with cosmic consciousness, to make choices that honor the extraordinary journey those atoms took to become you. In the end, supernova didn't just give us the elements of life, they gave us a story so epic, it challenges us to grow worthy of our stellar origins. Supernova might seem like distant, irrelevant explosions when it comes to Earth's climate, but their fingerprints are hidden in the planet's most dramatic shifts. Take the late Ordovician mass extinction, around 445 million years ago, a time when Earth plunged into an ice age so severe it wiped out nearly 85% of marine species. Geologists studying ancient rock layers found something unexpected, a spike in radioactive iron-60 isotopes, a telltale signature of a nearby supernova. This cosmic debris didn't just leave a mark in the rocks, it may have triggered a cascade of atmospheric changes. When high-energy particles from the explosion rained down on Earth, they could have ionized the upper atmosphere, sparking chemical reactions that depleted ozone and thickened cloud cover. Suddenly, sunlight struggled to reach the surface, temperatures dropped, and ice sheets spread a climate revolution with stellar origins. But supernova's influence doesn't stop at ice ages. Nitrogen oxides, generated when cosmic rays bombard the atmosphere, are potent greenhouse gases. A close enough stellar explosion might flood the skies with these compounds, creating short-term warming spikes before the cooling effects dominate. Evidence from Antarctic ice cores reveals mysterious nitrate surges dating back tens of thousands of years, some aligning with known supernova remnants. While these events pale in comparison to human-driven climate change, they reveal a startling truth. Earth's thermostat has never been entirely under terrestrial control. The universe itself occasionally reaches into our atmosphere and tweaks the dials. This cosmic perspective reframes how we think about climate stability. For all our fears about tipping points and feedback loops, Earth has always been subject to forces beyond its borders. The difference now is the timescale supernova operate on million-year cycles, while human activity has compressed what should be gradual shifts into mere decades. Yet there's a humbling lesson here. Just as ancient civilizations adapted to ice ages they couldn't comprehend, we're learning to navigate a climate system far more interconnected than we once imagined. The next time you hear about rising CO2 levels, remember, you're witnessing a planetary transformation with echoes of stellar cataclysms, a reminder that climate change, in one form or another, is written into the universe's grand narrative. The night sky may seem eternal, but hidden in its familiar patterns are stars teetering on the edge of catastrophe, and one of them could rewrite Earth's cosmic story before the century ends. Betelgeuse, the fiery shoulder of Orion, has been flickering unpredictably for years, sparking debates among astronomers. This red supergiant, just 640 light-years away, is a cosmic powder keg with a core burning through its final reserves of nuclear fuel. When it goes, and it will go, the explosion will be so bright it could outshine the full moon for weeks, casting eerie shadows on our nights. But here's the twist: despite its dramatic death throes, Betelgeuse poses virtually no threat to life on Earth. The real risks and revelations come from subtler corners of our galactic neighborhood. Take Rho Cassiopeiae, another unstable supergiant 3 times farther away, but packing 10 times Betelgeuse's explosive potential. Unlike Betelgeuse's predictable dimming, Rho Cassiopeiae has a history of violent outbursts, ejecting shells of material like a star preparing for its grand finale. Then there's Eta Carinae, a binary system so volatile it already died in the 1800s with a great eruption that made it the second brightest star in the sky for years. Modern telescopes reveal its hourglass nebula brimming with debris, a preview of the supernova to come. These aren't just ticking time bombs, they're cosmic laboratories, offering real-time glimpses into how massive stars behave when they're on borrowed time. The fascination isn't just about spectacle. When a nearby star explodes, its light will carry secrets about the death throes of massive stars, data we can't simulate in any lab. Neutrinos, those ghostly particles that stream through matter unimpeded, will arrive hours before the light, giving detectors like Super Kamiok and in Japan an early warning. This advance notice would let astronomers point telescopes in precisely the right direction, capturing the explosion's first moments in unprecedented detail. The last time humanity witnessed a Milky Way supernova was in 1604, when Kepler's star blazed brighter than Jupiter. Today, with orbiting observatories like Swift and Chandra, we'd see everything from gamma-ray flashes to the birth of a nebula, a front-row seat to stellar reincarnation. Yet the most tangible impact might be on Earth's upper atmosphere. Historical ice core samples reveal nitrate spikes coinciding with known supernova, evidence that these explosions can chemically alter our air. A close enough event within 30 light-years could temporarily punch holes in the ozone layer, increasing UV radiation at the surface, but the odds are vanishingly small. Statistically, a dangerously close supernova occurs only once every few 100 million years. The more likely scenario, a celestial light show for the ages, followed by a surge in PhD theses as astronomers dissect the data. What makes this waiting game so thrilling is the uncertainty. Stars don't announce their explosions with countdown clocks. Betelgeuse could detonate tomorrow or linger for another 100,000 years. This unpredictability turns every night of stargazing into a potential historic moment, a reminder that the universe doesn't operate on human schedules. For professional and amateur astronomers alike, that's the ultimate adrenaline rush, knowing that at any moment the sky might rewrite its own map, and we'll be here, telescopes ready, to witness the rebirth of the cosmos from the ashes of a dying star. Water, the shimmering blue essence of life on Earth, might seem like a purely terrestrial phenomenon, but its true origins lie in the fiery deaths of distant stars. Every drop in our oceans, every flake of polar ice, even the moisture in your breath carries atoms forged in supernova and distributed across the cosmos like celestial breadcrumbs. A prevailing theory suggests that Earth was born dry, a scorching rubble pile too close to the young sun for water to condense. So how did our planet become the blue marble we know today? The answer may lie in a cosmic relay race where supernova created the raw materials and comets, icy messengers from the outer solar system, delivered them to our doorstep. Consider the chemistry of a typical comet, a frozen mix of water ice, carbon dioxide, and complex organic molecules. When scientists analyzed the isotopic fingerprints of water in comets like 67P Churyumov-Gerasimenko visited by the Rosetta mission, they found a striking match to Earth's oceans. But here's the twist: that water didn't form in the comet itself. Its hydrogen atoms carry a specific ratio of deuterium, a heavier isotope that points to an origin in the frigid molecular clouds where stars are born. These clouds, enriched by supernova debris, became the nurseries where water molecules first assembled on dust grains, sheltered from destructive radiation by icy mantles. Over millions of years, those grains clumped together into comets, which later bombarded the young Earth during the late heavy bombardment period around 4 billion years ago. The role of supernova in this process is surprisingly hands-on. When a massive star explodes, its shockwaves don't just spread heavy elements, they also trigger chemical reactions in surrounding gas clouds. Lab experiments show that when silicate minerals common in stardust are exposed to supernova-generated hydrogen and oxygen under space-like conditions, they spontaneously form water molecules on their surfaces. This isn't just theoretical. The Herschel Space Observatory detected vast quantities of water vapor in the debris around supernova remnants like Cassiopeia A, proof that these explosions aren't just destroying, they're hydrating the cosmos. Yet the story gets even richer when we follow those water molecules to their next destination, protoplanetary disks. ALMA telescope images of young star systems reveal concentric rings where water ice has accumulated, often in staggering quantities. In the HL Tauri system, for example, the frozen water reserves in the outer disk could fill Earth's oceans thousands of times over. Crucially, these icy reservoirs are positioned beyond the snow line, the distance from a star where temperatures drop low enough for water to freeze. When planets form, gravitational interactions fling some of these ice-rich bodies inward, a delivery mechanism that might have turned arid worlds like early Earth into aquatic paradises. The implications for astrobiology are profound. If supernova-enriched comets routinely ferry water to inner planets, then habitable worlds might be far more common than we thought. Mars shows evidence of ancient waterways, while moons like Europa and Enceladus harbor subsurface oceans, all potentially filled by the same celestial plumbing that watered Earth. Even more intriguing, the organic molecules often found alongside water in comets' amino acids, sugars. Even the components of RNA suggest that supernova didn't just deliver the medium for life, but possibly some of the ingredients too. This cosmic perspective transforms how we see something as simple as a glass of water. What we're drinking isn't just H2O. It's a relic of stellar explosions, a testament to the universe's relentless recycling program. Every sip contains atoms that survived the unimaginable violence of a supernova, hitched a ride on a comet, and endured a 4.5 billion year journey to reach you. The next time it rains, remember, you're witnessing the final leg of water's epic voyage, a process that turned the ashes of dead stars into the lifeblood of our planet. Every time you take a step, the calcium strengthening your bones carries the echo of a dying star's final moments. That same calcium, along with the iron coursing through your veins and the phosphorus fueling your cells, began its journey in the unimaginable heat of a stellar explosion billions of years ago. These elements aren't just passive ingredients, they're active participants in the story of life, shaped by astrophysical processes that predate our solar system itself. Consider iron, the core component of hemoglobin that binds oxygen in your blood. This vital element can only form under the extreme pressures of a collapsing star's core, where temperatures exceed 100 million degrees. Without supernova violently dispersing these forged metals across space, Earth's geology, and by extension, our biology, would look radically different. The connection runs deeper than simple chemistry. The way these stellar-born elements function in our bodies reveals an astonishing cosmic efficiency. Take potassium-40, a radioactive isotope found in bananas and your own muscles. This element was created in supernova through rapid neutron capture, a process that only occurs during the most violent stellar deaths. Yet in your body, it plays a crucial role in nerve transmission and muscle contraction. Even more remarkably, the zinc in your immune system and the copper in your enzymes share this stellar origin. forming an elemental toolkit that evolution has harnessed with breathtaking precision. This interplay between astrophysics and biology becomes even more striking when we examine extremophiles organisms thriving in Earth's harshest environments. Deep-sea vent bacteria that metabolize sulfur, or radiotolerant fungi that repair DNA damage from cosmic rays, aren't just surviving, they're demonstrating how life adapts to conditions reminiscent of the violent stellar environments where their elemental components were born. The tungsten in some archaea's enzymes, forged in kilonovae, the selenium protecting your cells from oxidative stress, synthesized in red giant stars. Every biochemical process in your body is essentially stardust learning to sustain itself, a cosmic inheritance playing out in microscopic detail. What's truly humbling is the timescale of this elemental journey. The iron in your blood likely took over 1 billion years to reach the molecular cloud that birthed our solar system. It may have cycled through multiple stars and supernova before becoming part of Earth's core, then volcanic outgassings, then soil, then plants, and finally your bloodstream. This means when you cut yourself and see that familiar red hue, you're glimpsing a substance older than our planet, a relic of stellar alchemy that somehow became the vehicle for consciousness. The implications stretch beyond poetry. Modern medicine relies on these stellar elements. Technetium-99 for medical imaging comes from neutron star mergers, while radioactive cobalt-60 used in cancer treatment originates in supernova nucleosynthesis. Even our attempts to create artificial blood substitutes stumble on a fundamental truth. We're trying to replicate a solution the universe spent billions of years perfecting in stellar furnaces. This biological stellar connection isn't just philosophical, it's practical, guiding everything from nutritional science to space medicine as we prepare for interplanetary travel. Perhaps most remarkably, this elemental kinship suggests that any life elsewhere in the universe would share our stellar origins. Alien biochemistry might use different molecular structures, but the underlying elements, carbon, oxygen, nitrogen, would come from the same cosmic processes. In this light, the search for extraterrestrial life becomes a hunt for familiar stellar signatures in unfamiliar configurations. When we analyze exoplanet atmospheres for oxygen or methane, we're essentially looking for the waste products of stardust that learn to metabolize, a universal biology built from universal chemistry. This convergence of astrophysics and biology shatters traditional boundaries between scientific disciplines. The calcium in your bones connects you to supernova just as surely as telescopes connect astronomers to distant galaxies. Your very existence stands as proof that the universe isn't just hospitable to life, it's actively predisposed to create and sustain it, one stellar explosion at a time. Every breath you take, every thought you have, is literally made possible by stars that died so you could live. That's not metaphor, that's astrophysics written in flesh and blood. When a brilliant new star blazed across the sky in 1054 AD, the Anasazi people of the American Southwest didn't just see a celestial event, they witnessed a sacred messenger. High on a canyon wall in what's now Arizona, they painted a 10-pointed star beside a crescent moon, capturing the supernova that Chinese astronomers called the guest star in their own celestial language. Half a world away, Mayan astrologers charted the same cosmic light on bark paper codices, interpreting its sudden appearance as a shift in the divine order. These weren't primitive reactions to an unexplained phenomenon. They were sophisticated attempts to reconcile the heavens' abrupt violence with earthly existence, blending observation with cosmology in ways modern science is only beginning to appreciate. The Crab Nebula's progenitor star didn't just leave behind a glowing remnant, it ignited theological revolutions. In Japan, the 1054 supernova became linked to the legend of Terra no Masakoto, a slain samurai whose restless spirit was said to manifest as the fiery, vengeance star. Medieval Islamic scholars like Ibn Sina recorded the event as evidence of celestial mutability, challenging Aristotelian ideas of an unchanging cosmos that had dominated Christian and Islamic thought for centuries. Even the biblical book of Revelation's description of a star called wormwood falling from heaven may encode cultural memories of supernova visible to Mediterranean civilizations, their sudden brilliance interpreted as divine portents. What makes these interpretations so fascinating is their universality. Norse mythology's Ragnarök, a cataclysm where the sky darkens and stars vanish, bears uncanny resemblance to supernova light echoes fading over generations. Aboriginal Australian oral traditions speak of ancestral spirits rearranging the stars during dream time, with some researchers suggesting these stories preserve observations of prehistoric supernova. In every case, cultures separated by continents and millennia arrived at similar conclusions. When the heavens changed dramatically, it signaled a reordering of earthly and spiritual realms. This intersection of astrophysics and belief isn't just historical. Modern telescope surveys reveal that the 1054 supernova occurred in a constellation laden with symbolic meaning across cultures: Taurus, the bull. To ancient Egyptians, Taurus housed the soul of Osiris. To Hindus, it marked the start of creation. That a stellar explosion would manifest in such culturally charged space feels less like coincidence and more like cosmic poetry. Today, as astronomers use indigenous star names and incorporate oral histories into supernova research, we're witnessing a renaissance of these ancient dialogues where science doesn't dismiss ancestral knowledge but collaborates with it to reconstruct celestial events. Perhaps no tradition captures this synergy better than the Buddhist concept of Indra's net, where the universe is imagined as an infinite web with jewels at each intersection, each reflecting all others. A supernova, in this framework, isn't an isolated explosion but a vibration felt across the cosmic web, an idea eerily resonant with modern astrophysics' understanding of how these events chemically enrich entire galaxies. Whether through 14th century Tibetan astronomers tracking marvelous stars or contemporary physicists modeling nucleosynthesis, humanity's quest to understand stellar cataclysms remains, at its core, a search for connection between Earth and sky, between destruction and creation, between the atoms in our bodies and the stars that forged them. This enduring dialogue between stellar phenomena and human meaning-making reveals something profound. Our ancestors weren't wrong to see divinity in supernova. They simply used different language to describe what we now call astrophysics. The awe they felt watching a new star outshine Venus is the same awe that grips modern scientists when Chandra's X-ray vision captures a neutron star's birth. Both responses recognize something transcendent in these explosions, not as supernatural acts, but as natural processes so magnificent they blur the line between the physical and the sacred. In the end, whether carved on canyon walls or encoded in supercomputer simulations, humanity's supernova stories all whisper the same truth. We are witnesses to a universe capable of terrifying destruction and breathtaking creation, often in the same fiery breath. For all the dazzling breakthroughs in astrophysics and astrobiology, we've barely scratched the surface of understanding supernova's full role in life's origins. Consider this: we've catalogued thousands of supernova across the cosmos, yet we've never witnessed one in our galaxy with modern instruments. The last Milky Way supernova visible to the naked eye occurred in 1604, before telescopes could capture its spectra or neutrinos. This means much of what we know about these explosions comes from distant observations or computer simulations, leaving gaps in our understanding of their immediate chemical and biological impacts. Take the mystery of chiral molecules, for instance, organic compounds that come in left-handed and right-handed versions. Life on Earth exclusively uses left-handed amino acids, and no one knows why. Some theories suggest supernova polarized light could have influenced this preference, but without observing a nearby explosion's effects in real time, the puzzle remains unsolved. Even more perplexing are the gaps in nucleosynthesis models. While we've mapped how stars forge elements up to iron, the origins of heavier metals like gold and platinum still spark debates. Kilonovae colliding neutron stars are prime suspects, but recent lab experiments hint that certain rare supernova might also contribute. Then there's the enigma of phosphorus, a life-critical element that's curiously abundant on Earth compared to cosmic averages. Did a particular type of supernova shower our solar system with extra phosphorus, or did some undiscovered interstellar chemistry amplify its presence? The answers could redefine our search for habitable exoplanets, yet they elude us. Perhaps the most humbling frontier is the unknown unknowns, processes we haven't even thought to consider. Before the 1980s, no one imagined that supernova shockwaves could synthesize complex organics on dust grains. Now it's textbook science. What other transformative mechanisms might we be missing? Could supernova produce exotic biomolecules we haven't detected? Might their magnetic fields or neutrino bursts play hidden roles in prebiotic chemistry? The universe has consistently proven stranger than our boldest theories, and that pattern shows no sign of breaking. This uncertainty isn't a failure, it's the engine of discovery. Every unresolved question, from the peculiar isotopic ratios in meteorites to the bizarre behavior of pre-supernova stars like Betelgeuse, represents a doorway to new science. The James Webb Space Telescope recently detected organic molecules in a supernova remnant younger than our solar system, a finding that upended assumptions about how quickly life's ingredients could assemble. Similarly, labs recreating interstellar ices keep stumbling upon unexpected reactions, like the spontaneous formation of ribose, the sugar in RNA under simulated supernova conditions. These surprises remind us that the cosmos still holds cards close to its chest. What keeps scientists awake at night isn't just the gaps in knowledge, but the tantalizing possibility that we're overlooking entire chapters in the story of life's cosmic origins. Imagine if supernova don't just spread elements but also catalyze their assembly into complex structures we haven't thought to look for. Picture a scenario where the very explosions that sterilize nearby systems also seed them with pre-packaged chemical networks like cosmic starter cultures. Far-fetched, perhaps, but so was the idea of Stardust becoming self-aware until we found ourselves here, pondering it all. The beauty of this uncertainty is how it propels us forward. Every unanswered question about supernova and life's origins isn't a dead end. It's an invitation to build better telescopes, design more sensitive detectors, and dream up bolder experiments. From drilling deeper into Antarctic ice for supernova isotopes to developing AI that can predict stellar collapse, the tools to solve these mysteries are taking shape. And when the next galactic supernova finally arrives, whether in our lifetime or centuries hence, it won't just light up the sky. It'll illuminate the next great leap in understanding our elemental kinship with the stars. Until then, the questions themselves guide us, reminding that science at its best is a conversation with the unknown. One evening in August 2023, an amateur astronomer in Japan named Koichi Itagaki pointed his backyard telescope at the familiar Pinwheel galaxy and noticed something extraordinary, a star where none had been before. Within hours, telescopes worldwide swiveled toward his discovery, a brilliant supernova erupting 21 million light-years away. Itagaki wasn't part of a prestigious research institution. He was a former printing company employee whose passion for the night sky had already led him to uncover over 100 stellar explosions. His story isn't unique. Nearly 1/3 of all supernova discoveries in the past decade have come from amateur astronomers, proving you don't need a PhD or $1 million observatory to contribute to cutting-edge astrophysics. What makes these citizen scientists so effective? Unlike professional telescopes booked months in advance for specific research, amateurs can scan hundreds of galaxies nightly, free to chase hunches. Their smaller telescopes often have wider fields of view, making them ideal for spotting sudden bright spots in familiar galactic neighborhoods. Take the case of 10-year-old Catherine Gray from Canada, who in 2011 became the youngest person ever to discover a supernova. Using images from her father's amateur setup, she identified a telltale speck in the constellation Camelopardalis that experts had missed. These discoveries aren't just luck, they're the result of meticulous training. Online platforms like the American Association of Variable Star Observers teach volunteers how to compare telescopic images for subtle changes, turning stargazers into cosmic detectives. The impact goes beyond tallying explosions. When amateur networks like the All-Sky Automated Survey for Supernova detect an event, they trigger automated alerts to professional observatories. This rapid response allows scientists to capture critical early data, like the shock breakout phase when a supernova's light first pierces the star's surface, a fleeting moment that holds clues to the progenitor star's structure. In 2017, amateur sightings of supernova 2017 EU in the Fireworks Galaxy enabled NASA, a swift satellite, to begin observations within hours, revealing unexpected ultraviolet flares that reshaped models of stellar death throes. Technology has democratized discovery further. Free software like AstroImage lets anyone analyze telescope data, while projects like Zooniverse's Supernova Hunter invite the public to sift through millions of galaxy images from robotic surveys. Sometimes the human eye spots what algorithms miss, like the peculiar supernova 2014 J in Messier 82, first noticed by a British teaching assistant reviewing public data from an online telescope. These collaborations are rewriting astronomy's social contract. No longer just passive consumers of science, the public now actively shapes it, blurring the line between professional and amateur in the best possible way. The ripple effects extend beyond academia. When a retired electrician in Argentina or a high school teacher in South Africa makes a discovery, it inspires entire communities. Local news coverage of amateur supernova hunters often sparks surges in astronomy club memberships, creating new generations of science enthusiasts. There's something profoundly egalitarian about the idea that a teenager with a modest telescope might glimpse a stellar explosion before anyone else on Earth, a reminder that the universe doesn't discriminate between credentials when offering up its secrets. Perhaps the most beautiful aspect of this partnership is how it mirrors the supernova themselves. Just as these explosions enrich galaxies with elements for future stars, citizen science enriches our collective understanding, scattering knowledge like cosmic seeds. Every time an amateur astronomer reports a suspicious speck of light, they're participating in a tradition that stretches back to the earliest skywatchers, proving that curiosity, not equipment or titles, is the true engine of discovery. And in an era when professional astronomy grows increasingly specialized, these backyard observers keep the field grounded, reminding us all that the night sky belongs to everyone. The idea of multiple universes isn't just science fiction, it's a serious scientific hypothesis that could rewrite everything we know about supernova and life itself. Imagine a parallel cosmos where the laws of physics differ slightly, where stars burn hotter or cooler, collapse faster or slower. In such a universe, supernova might be far more frequent, scattering heavy elements like cosmic confetti, or so rare that planets form with barely enough carbon or iron to kickstart biology. This isn't idle speculation, it's a frontier question in theoretical physics, one that challenges our understanding of life's cosmic prerequisites. Take the concept of the multiverse, where countless universes bubble into existence, each with its own unique set of physical constants. Some might have stronger nuclear forces, causing stars to explode more violently and frequently, seeding space with an overabundance of heavy metals. Others could have weaker gravity, preventing massive stars from forming altogether, leaving their galaxies starved of the elements life depends on. The staggering implication. Our universe's Goldilocks supernova rate frequent enough to enrich planets, but not so frequent as to sterilize them, might be vanishingly rare in the grand cosmic landscape. This raises a provocative question. If life requires a precise balance of stellar explosions, how many universes actually hit the sweet spot? Simulations of alternative physics suggest that even minor tweaks to fundamental constants could render supernova ineffective at dispersing heavy elements. In some scenarios, stars might collapse directly into black holes without exploding, locking away life's building blocks forever. In others, supernova could be so energetic they shred nearby planetary systems before life can take hold. Our universe's delicate equilibrium, where supernova act as both creators and destroyers, might be the exception rather than the rule, yet there's an even wilder possibility. Some theorists propose that universes with radically different physics could host entirely unfamiliar forms of life, built not from carbon and water, but from exotic elements forged in alternate stellar processes. Imagine a world where silicon-based organisms thrive in supernova, enriched environments too harsh for Earth like biology, or where life exploits the turbulent chemistry of hypernova remnants. If true, astrobiology wouldn't just be the study of life's origins, it would be the study of infinite origins, each tied to its universe's unique stellar life cycle. The multiverse theory also casts Earth's history in a new light. Our planet's position in the Milky Way's quiet suburbs, its timing between nearby supernova, even the specific isotopes that make up our bodies, all might be the result of a cosmic lottery we didn't know we were playing. It's humbling to consider that in another universe with slightly different laws, the atoms now reading these words might never have formed at all. While we can't yet observe other universes, clues might lie closer to home. Anomalies in our own cosmic microwave background or unexplained elemental abundances could hint at collisions with other universes, each with their own supernova legacies. Until then, the multiverse remains a tantalizing thought experiment, one that transforms supernova from mere astrophysical events into cosmic litmus tests, revealing whether a universe is cursed with sterility or blessed with the conditions for life. And if ours is one of the lucky ones, it makes the stardust in our veins all the more extraordinary. Picture a classroom where students aren't just memorizing the periodic table, they're tracing each element back to its explosive stellar birthplace. Education transforms the abstract saga of supernova into something tangible, something alive. When a 12-year-old learns that the oxygen they breathe was forged in a dying star, it's not just a science lesson, it's an awakening to their own cosmic ancestry. Programs like NAS, a universe of learning, harness this power, turning supernova remnants into interactive 3D models that students can explore with VR headsets. peeling back layers of gas to reveal the hidden chemistry of life's origins. These aren't just tools, they're time machines, collapsing billions of years into moments of visceral understanding. Teachers worldwide are rewriting curricula to reflect this interconnected story. In Australia, educators use Aboriginal astronomy to frame supernova as celestial ancestors, blending modern astrophysics with 40,000-year-old star knowledge. Meanwhile, in Chile, high school students analyze real telescope data from the Atacama Desert, hunting for supernova remnants in the same skies their ancestors once mapped. These approaches do more than teach facts, they cultivate cosmic literacy, the ability to see Earth as part of a dynamic, element recycling universe. When a student builds a spectrometer from cardboard tubes to analyze starlight, they're not just learning physics, they're retracing the steps of Cecilia Payne-Gaposchkin, the astronomer who first connected stellar composition to Earth's chemistry. The ripple effects extend beyond classrooms. Citizen science projects like Zooniverse's Supernova Hunters invite kids as young as 8 to scour telescope images for stellar explosions, with several making verified discoveries. In rural India, mobile planetariums project supernova simulations onto monsoon-proof inflatable domes, reaching villages where textbooks are scarce but curiosity burns bright. Even toys are getting smarter. Companies now sell DIY supernova kits with safe chemicals that mimic nucleosynthesis, letting children create their own stellar explosions in test tubes. Universities are taking note. Astrobiology programs once reserved for graduate students now appear in undergraduate catalogs, with courses like Stellar Alchemy and the Origins of Life filling lecture halls. At Arizona State University, students can handle actual meteorites in their introductory astronomy labs, feeling the weight of stardust in their palms. These experiences plant seeds like the University of Tokyo student who developed a new method to date supernova remnants after being inspired by a childhood planetarium visit. The most transformative work happens at the intersection of art and science. In Brazil, street artists muralize supernova remnants alongside QR codes linking to astrophysics lectures. The London Symphony Orchestra recently performed a symphony composed from supernova light curve data, translating stellar death throes into music. When a teenager in Nairobi sees her own poetry about stardust projected alongside Hubble images at a community science fair, she's not just learning about the cosmos, she's contributing to its story. This educational revolution faces challenges, of course. Budget cuts threaten planetarium funding, and misinformation competes with rigorous science. But the solution lies in the very nature of what's being taught. Supernova remind us that destruction precedes creation. Underfunded schools are partnering with local astronomers to turn smartphone cameras into rudimentary telescopes. Teachers in war zones use the Crab Nebula's expansion rate to teach geometry, proving that even amid earthly chaos, the stars remain a universal classroom. The ultimate goal isn't to create millions of astronomers, it's to nurture a generation that sees the world through a cosmic lens. When a future doctor understands that the calcium in bones was forged in stellar explosions, they approach medicine with newfound reverence. A policymaker who grasps Earth's rarity in a supernova-sculpted galaxy may prioritize environmental protection. Even those who never enter STEM fields carry forward this perspective, seeing themselves not as passive observers but as active participants in an unfolding cosmic drama. Perhaps this is supernova's greatest gift to education. They dissolve the illusion of separation between humanity and the universe. Every lesson about these stellar explosions is secretly a lesson about interconnection, a reminder that the same forces that light up the cosmos also light up the neural pathways of a child discovering them for the first time. And in that spark of understanding, the cycle continues. Stars die, knowledge spreads, and the universe keeps writing its story through minds young enough to still wonder why. The next decade of space exploration is poised to turn supernova from distant spectacles into intimate laboratories, with missions designed to dissect these cosmic explosions atom by atom. At the forefront is NASA's proposed Habitable Worlds Observatory, slated for launch in the 2030s. Unlike any telescope before it, this instrument won't just capture stunning images of supernova remnants, it'll analyze their chemical fingerprints with unprecedented precision. Picture this: by studying the infrared glow of specific elements like phosphorus or molybdenum in debris clouds light years away, scientists could reconstruct entire nucleosynthesis pathways, revealing exactly how dying stars forge the building blocks of life. The telescope's coronagraph will even block out starlight to spot newborn planets forming in the aftermath of these explosions, letting us watch solar systems being built from stellar ashes in real time. But the real game changer might come from the European Space Agency's Theseus mission, a spacecraft designed specifically to catch supernova in the act. Equipped with gamma-ray burst detectors and rapid response spectrographs, Theseus would act as a cosmic paramedic, arriving on the scene within hours of a stellar explosion to document its earliest moments. These critical minutes when shockwaves first tear through a star's outer layers hold secrets about how heavy elements get catapulted into space. The mission's ability to monitor the entire sky every few days means it could catch hundreds of supernova yearly, building a statistical map of stellar deaths across different galaxy types and cosmic eras. Imagine comparing element production in the metal-rich galaxies of today versus the pristine ones of the early universe, a test of whether life's chemistry was predestined or a lucky accident. Meanwhile, in labs across Earth, scientists are preparing for an even bolder leap: interstellar probes to nearby supernova remnants. Concepts like NASA's Interstellar Probe, aiming for a launch before 2050, could target structures like the Crab Nebula, a sprawling debris field from a star that exploded roughly 8,000 years ago. Flying through these nebulae at a fraction of light speed, onboard mass spectrometers would directly sample dust grains containing presolar material, analyzing isotopes too delicate to detect remotely. Some of these grains predate our solar system, making them time capsules from the very supernova that seeded our cosmic neighborhood. The data could settle long-standing debate, like whether our sun formed in the shadow of multiple stellar explosions, or if one particularly nearby supernova delivered an extra dose of life-critical elements. Private initiatives are joining the hunt too. The Breakthrough Starshot project, famous for its nanoprobe concepts, has proposed sending laser-propelled chips to Alpha Centauri, but the same technology could revolutionize supernova studies. A swarm of gram-scale probes, each carrying specialized sensors, might be scattered through a supernova remnant like cosmic confetti. Some could measure magnetic fields crucial for element transport, while others analyze radiation's impact on precursor molecules for life. At a fraction of traditional mission costs, this approach could provide multi-point observations impossible with single spacecraft. The most visionary proposals come from astrophysicists dreaming beyond conventional telescopes. A team at the University of Chicago is developing plans for neutrino observatories in lunar orbit, capitalizing on the Moon's lack of atmosphere to detect these ghostly particles from supernova with unparalleled clarity. Since neutrinos escape a dying star hours before light, such detectors could provide early warnings to swing telescopes toward impending explosions. Other researchers advocate for space-based gravitational wave detectors tuned specifically to supernovas' unique frequencies, listening for the literal ripples in spacetime as massive stars collapse. What makes these missions extraordinary isn't just their technology. but their potential to answer existential questions. By mapping how supernova debris mixes with molecular clouds, we might finally understand why some stellar nurseries birth life-friendly systems while others remain barren. Spectroscopic studies of freshly synthesized organic molecules in supernova ejecta could reveal whether the universe prefers certain biochemical pathways. And if probes like Interstellar find evidence that our solar system benefited from an unusually rich supernova delivery, it would suggest that Earth's fertility isn't universal, but the product of specific, perhaps rare, cosmic circumstances. These missions also prepare us for the ultimate astronomical event, the next Milky Way supernova. When Betelgeuse or another nearby star finally explodes, this fleet of advanced instruments will be ready to capture every neutrino, gamma ray, and elemental emission, transforming a celestial light show into the most detailed astrophysical experiment in history. The data could rewrite textbooks on everything from nuclear physics to astrobiology, all while reminding us that humanity's quest to understand stellar death is, ironically, one of the most vibrant areas of scientific exploration. As these telescopes and probes come online, they won't just study supernova, they'll trace the lineage of life itself, from the violent hearts of dying stars to the delicate chemistry of habitable worlds. Each new observation adds another thread to the tapestry connecting cosmic destruction to biological creation, proving that the universe's most catastrophic events might also be its most creative. The era of passive observation is ending. We're about to become active participants in unraveling the stellar alchemy that made our existence possible. From the ashes of dying stars to the DNA in your cells, this cosmic connection isn't just science, it's poetry written in the language of physics. Every atom in your body carries the echo of a stellar explosion, a story that began billions of years before the first microbes stirred on Earth. But this revelation isn't merely about chemistry, it's about perspective. When you realize the oxygen in your lungs was forged in a star's final, cataclysmic moments, the universe stops feeling vast and indifferent. It becomes intimate, almost purposeful. That calcium strengthening your bones, it survived a journey through superheated gas clouds, asteroid collisions, and volcanic eruptions just to become part of you. This knowledge changes how we see ourselves. You're not just an observer of the cosmos, you're its living archive. The iron in your blood, the phosphorus fueling your thoughts, even the zinc boosting your immune system, they're all fragments of ancient stars that died so life could begin. It's humbling to think that the same forces capable of obliterating solar systems also painstakingly assembled the ingredients for biology. Supernova don't just light up galaxies, they're cosmic alchemists, turning simplicity into complexity, chaos into order. And we, every person, every tree, every hummingbird, are their most astonishing creations. Yet this story isn't finished. With every meteorite analyzed and every supernova remnant mapped, we're adding new chapters. Imagine what we'll discover next. Perhaps evidence that stellar explosions directly seeded Earth with probiotic molecules, or proof that other solar systems inherited even richer elemental gifts than ours. The James Webb Space Telescope is already spotting organic molecules in distant nebulae, while labs on Earth simulate how stardust could spontaneously form cell-like structures. We're on the verge of answering whether life is a cosmic fluke or the universe's secret agenda. So when you step outside tonight and gaze at the stars, remember, you're not looking up at the universe. You're looking into it like a mirror reflecting your own celestial heritage. Those flickering lights aren't just distant suns, they're the factories that built you, the ancestors of your atoms. And if this exploration has sparked your curiosity, you're already part of the next great adventure, the ongoing quest to understand how stardust became sentient. Share your wonder in the comments and join us as we keep unraveling the cosmos' grandest story. Don't forget to subscribe, because the universe still has countless secrets left to